Welcome back, students. Let's look at the fourth technique now. Till now, we've learned about direct substitution, factorization, and rationalization. Now, we're going to learn about something really interesting. It's called the sandwich theorem. Interesting name. It is also known as the squeeze theorem. Let's look at what the theorem says. It says that if f of x, g of x, and h of x are three functions that are defined over an interval, the same interval, such that f of x, the value of f of x always falls between the value of g of x and h of x for any x, then if you are able to find out the limit of g of x and you are able to find out the limit of h of x and they are equal, the limit of f of x is also going to be same as the limit of h of x and g of x. Well, that's the statement, but let's try to understand it piecewise, slowly. This is our function f of x, right? We can see that f of x is lying between h of x and g of x. Would it be right to say that for any value of x, f of x value will always be between h of x and g of x's value? Once again, would it be right to say that the value of f of x will always fall between the values of h of x and g of x for any x? Let's say I choose x equal to 1. For this x, have a look at it. Whatever the value of f of x is, that's between the value of h of x and g of x, isn't it? That's what is given here. So for whatever interval I, we've defined these three functions. Let's say this entire interval is the interval I. This is the domain of the three functions. Now, in this entire domain, f of x's value always lies between h of x and g of x's value. Sometimes they may be equal as well, and that's why we have this equality sign here. Okay, so g of x is less than equal to f of x and f of x is less than equal to h of x. If we have such a condition, and we have one more condition, which is that limit of h of x and limit of g of x coincide. Now if you look at this point A, at this point A, limit of g of x coincides with limit of h of x, isn't it? Whatever is that value, that value is indicated as L. So if we have these two conditions, first condition is that f of x always lies between g of x and h of x. In other words, f of x is sandwiched between h of x and g of x. And the limit of h of x and g of x are equal at some value of x. In such cases, the limit of f of x at that point A will also be equal to L. As simple. It's pretty simple, right? By looking at the figure, we all can understand. See, f of x is sandwiched between h of x and g of x. And if h of x and g of x are squeezing and they're becoming equal to one value, then the value of the function which is sandwiched between these two functions will also be the same, isn't it? So that's the theorem. It's called the sandwich theorem, also the squeeze theorem, because f of x is squeezed in between h of x and g of x. How does this theorem help us find out the limits? We'll see in a moment. We're going to apply this squeeze theorem on this limit. Now, we have a function f of x equal to x squared sine of 1 upon x. Try using direct substitution. See what you're getting. We're getting 0 into sine of 1 upon x. Well, Sine of 1 upon x. 1 upon x is a very, very large quantity. Sine of that quantity I cannot figure out because I do not know the value of my angle. If I don't know my angle, how can I figure out the sine of that angle? So if I can't figure out this entire thing is indeterminate to me. I cannot determine its value, so it's indeterminate. So direct substitution is definitely not working. There's no way to factorize this. Rationalizing again will not work because there is no square root. I can't see any root, under root sign here. So three techniques are out of the window. Let's try something else, which is the squeeze theorem. How do we apply this? Pay close attention. Look at the right hand side. There's a hint given to you. The hint says that if we plot sine theta, I'm sure you all know this is how the graph of sine theta looks like. Sine theta is a bounded function, okay? Its value fluctuates between two extremes. Such functions are called bounded functions. Can you identify those two extremes? So the value of sine of anything will always lie between -1 and +1, isn't it? The value of sine of anything will always lie between these two numbers. How is that going to help us? We're going to construct a function from this inequality. To use the squeeze theorem, the first step is to figure out an inequality from somewhere. Now we've got this inequality. The next part is use this inequality to construct our original function. Okay, all right, let's do that. So sine theta lies between -1 and 1. What can you tell me about x square times sine theta? X square times sine theta. What can you tell me about that? X square sine theta would lie between -x square and x square. Isn't it? What we have done is we've used the same inequality, just multiplied x square everywhere. Okay. Does this part look something similar to our squeeze theorem or the sandwich theorem? In the sandwich theorem, we saw that if f of x satisfied two conditions, f of x lied between g of x and h of x, and the limits of g of x and h of x are the same. Limit of g of x and limit of h of x were the same, where x was tending to 0 or any value, in this case 0. Okay, so if x was tending to a, if this was the same, I'm going to show you something here now. Can I call this thing as g of x, this thing as f of x, and this thing as? From here, we see that limit of g of x and limit of h of x coincide. Can you find out the limit of -x squared? Let's find out the limit of -x squared when x tends to 0. It's 0. Direct substitution helps us figure that out. What about limit of x squared when x tends to 0? This is also 0. Simple direct substitution will help you solve that. So limit of g of x and limit of h of x are coinciding. So what will be the limit of f of x? From here we can say, using the squeeze theorem or the sandwich theorem, you can say that limit of f of x is also 0 as x tends to 0. So this is our answer. Limit of f of x is equal to 0 as x tends to 0. Now, some of you will notice one thing, that the function looks a little bit different from what is originally there. So here I have sine of 1 upon x, whereas here I've taken sine theta. Doesn't matter. Basically, this says if you take sine of anything, okay, sine of anything is still bounded, right? So if you don't want to work with theta and you don't want to introduce a new variable, you can say simply sine 1 upon x will always lie between minus 1 to 1, right? Sine 1 upon x will always lie between minus 1 to 1. Use this inequality and then you will get 1 upon x everywhere, and you will get the identical function. So that's how we do it. Let's verify our answers using graphs. Remember this part though, that the function given to us is sandwiched between minus of x square and plus x square. Can you tell me how the graph of y equal to minus x square will look like? Think. While you are at it, also think how the graph of x square looks like. We all know that these are going to be parabolas. So concave up parabola is your x square or plus x square. Concave down parabola is your h of x equal to minus of x square. We have two functions, and in the middle we have actually our original function, which is x square into sine 1 upon x. It goes like this, and finally like this. At x equal to 0, look at what is happening. H of x is also tending to 0. G of x is also tending to 0. And f of x is lying between these two functions, so it must tend to 0. There is no other option for this function. And that's why limit of x square sine 1 upon x, it's going to be 0. Okay? So here's a strategy on how to use the squeeze theorem or the sandwich theorem. The first thing you do is you construct an inequality like we did. Sine theta always lies between minus 1 and plus 1. That was an inequality we constructed. Something similar to that. So the first step you do is you construct an inequality from somewhere. Okay, look at the function. If you're able to figure out an inequality, that means you will be able to apply the squeeze theorem. Then modify the inequality to arrive at the function given in the question. That would be your step 2. Step 1 would be to just create an inequality. Okay, just create an inequality. Get it from somewhere. Think of something, get an inequality. Second step, modify that inequality. Either multiply something to all the terms, divide something to all the terms, add something to all the terms, and so on. Do some algebraic manipulation and get f of x to resemble the exact function that is given in the question. Once you have done that, you have three functions actually. You have something like this, f of x bounded between g of x and h of x. You have something like this. So once we have modified the inequality and arrived at the function exactly given in the question, now we evaluate the limits of the two bounded functions, the function appearing to the left of f of x and the function appearing to the right of f of x. So you find the limit of g of x, you find this, and you also find the limit of h of x. This is your third step. Okay, so this is the third step, that you find the limit of g of x and the limit of h of x, the two bounding functions. Once we've completed the third step, the final step is just apply the statement of the squeeze theorem, which is, if we know that the limit of g of x is L and we know that limit of h of x is also the same number, the same quantity, you just apply the squeeze theorem and claim that limit of f of x is also going to be the same. Okay, and we are done with finding the limit, and we're done with the fourth technique, which is application of squeeze theorem or the sandwich theorem. But let's practice a question on this. We have a function 2 plus 2x squared sine of 1 by x, and we want to find out the limit using the squeeze theorem. Again, we can get started with the very first step, which is construct an inequality so that f of x is in between some numbers. Okay, so now which of these is a bounded function? Sine theta or sine 1 by x is always going to lie between -1 and 1. That is what we know. So let's write down the inequality. Step 1. Sine of anything literally will always lie between -1 to +1, -1 to 1, okay? Step 2 is try to arrive at the function given in the question. Step 2 is you keep multiplying, adding something or the other to finally arrive at this thing. And how do we do that? Let's multiply 2x square to all these three quantities. So 2x square times sine 1 upon x. So 2x square has to be multiplied with 1 also. So this is here, and here you'll get minus 2x square. Okay. But this is not the function that is given. I have an extra term which is plus 2, as you can see. So what I'll do is I'll add 2 on all the sides. So add here, add here, add here. And now look at the function in the middle. Isn't this the same thing as has been given to us? So 2 steps done. What was the third step? The third step was that we evaluate the limits of the two bounds. What are the two bounds? It's this one and this one. Can you evaluate the limits of these two? Limits x tending 0. Whatever is in the question, we have to focus on that value of x. So limit minus 2x squared plus 2 when x is tending to 0 is what? Just use direct substitution. 2 into 0 square plus 2, which will give you this number. Now let's look at the limit of this quantity, this function. Limit x tending 0, 2x squared plus 2. Just put the value of x, use direct substitution, you'll again find this is the answer. So step 4 and the final step is, you say, using the sandwich theorem or the squeeze theorem, whichever name you prefer. Using this theorem, you can claim that limit f of x, I'm calling this function as f of x, okay? Limit f of x as x tends to 0 is also 2. This is your answer, and we are done. Okay, so this was our fourth technique of finding limits using the squeeze theorem, the sandwich theorem. Let's practice one more question, okay? So one thing I want to tell you that squeeze theorem uh, mainly works when we have algebraic functions multiplied with either logarithmic functions or trigonometric functions. So we have a question now, an interesting looking question, but this time the graph of something is given to us. Okay, the graph of this much is given to us. This kind of tells me how to approach the question. I see that in this function we have an algebraic function multiplied with a logarithmic function, and I'm not able to figure out the exact value of the limit by direct substitution. Factorization, rationalization, not going to help us. The next technique is the squeeze theorem. So let's try the squeeze theorem. The first step was to create an inequality. Since the graph of this function, this part is given to us, can I say e to the power minus 1 upon x squared lies between two quantities, lies between something. Can I say that? So, can I say that e to the power minus 1 upon x squared lies between some quantities? Can I say that? Look at the graph and tell me if you're able to figure that out. See, this graph is definitely bounded, we can see, okay, bounded between these two numbers. So this number is 1 and this number is 0. So it lies between 0 and 1. We can see that because it's given in the question, so we don't have to worry too much. It's given in the question. The graph is given in the question. From the graph, we figured out the inequality. Step 2 was to somehow get the original function by doing some algebraic manipulation. And we can see that our original function is this. All we need to do is multiply x to the power 5 everywhere. Minus 1 upon x squared. This is x to the power 5 here. And this is 0 into x to the power 5, always going to give us 0. So this is what we have. So step 2 is also done. Step 3. Step 3 was to figure out the limits of the bounding functions. So limit of this thing, limit of 0 as x tends to 0, well, no brainer, it's 0. Limit of x to the power 5 as x tends to 0, 0 to the power 5, 0 again. What do we see? Limit of g of x and limit of h of x is coming out to be the same, and the value is 0. Well, it's a coincidence that all the two questions that we did, the limit were coming out to be 0, but using the squeeze theorem, we do get finite limits as well. So don't think that whenever you have to use the squeeze theorem, the answer is going to be 0 always. No, that's not true. Okay, anyway, let's proceed to the step 4 now. Step 4. We know the limit of the two bounding functions. You just say using squeeze theorem x to the power 5 e to the power minus 1 upon x squared as x tends to 0 is going to be the same number, this number. Okay, that's our answer. Okay, we have a couple of more questions, a couple of more practice questions on using the sandwich theorem. If you want, you can go through those examples as well. If you think you've understood the squeeze theorem perfectly well, you can move on to the next section, which is the L'Hopital theorem. That's another way of finding out limits. Okay. Okay, for the others who want more practice, let's move on to the next question. See, we've been doing the squeeze theorem and we all know that squeeze theorem is what's going to work here. So I'm not going to waste too much time, doing direct substitution and factorization and rationalization and then figuring out that all those things do not work. Let's just jump right into it. We're going to use the squeeze theorem to solve this question. We have to figure out the inequality first. Let's work on that. Cos of 1 upon x, cos of anything, would again fall between -1 and 1. What can you say about cos square of things? What would be the two bounds of cos square theta? Cos square, it's always going to be a positive number. It's always going to give you a positive number. And if the maximum of cos theta is 1, maximum of cos square theta is also going to be 1. Okay? But it's never going to be negative. So cos square anything is always going to lie between 0 and 1. So step 1 is done. Next part is multiply something in order to get the original function which resembles the function given in the question. So we have x cube that we're going to multiply with cos square 1 upon x. So that means x cube has to be multiplied here also. That means x cube has to be multiplied on this side also. So 0 into x cube is essentially 0. So I'm just going to write 0 there. 0. Okay. So this is our inequality. Now let's try to figure out the limits of the two bounds. Its limit is going to be 0 no matter what is the value of x we are approaching. So limit of this is 0. What about limit of x cube as x tends to 0? Again 0. So through that, finally using the squeeze theorem, we can claim that if I'm calling this as f of x, using squeeze theorem, I can say that limit of f of x as x tends to 0 is equal to limit of g of x and h of x as x tends to 0, which is this number. All right. Okay, so in the next session, we're going to look at the L'Hopital rule of finding out limits. And that's the fifth technique we are going to learn. Also, the L'Hopital rule would be easier to understand for those students who already know differentiation. If you do not know differentiation, then I would suggest you skip this part. Whenever you cover differentiation, you come back to this part and then watch the L'Hopital rule technique of finding out limits. Thank you so much for joining, students. See you again.